But before we go to QMRMR, we have to do something. We have to look at a third classification system, which has lost much of its relevance. But there are a few things in life which you need to do before you go further. Such is the contribution of this man called Karl Terzaghi. He was the first one to give a very, very usable kind of classification system, 1946. And that's why we need to start any discussion on classification method has to start with a mention of Karl Terzaghi. He was concerned that the design engineers are struggling to design tunnels. So if I could give them a simple approach, they don't have much input parameter, etc. And what he did, you see, if you tell the design engineers that here's a tunnel, and the tunnel, when you build the tunnel will be under so much load. So once they know the load or the pressure, they can design the support system to take care of that pressure. So what he did, he gave that pressure in terms of rock load factor, HP. So he said that depending on your condition, that size of the tunnel, the ground condition, etc., you can find out the HP factor. What is HP? The height of rock mass whose weight will come on the tunnel, so that you can design the tunnel. How to arrive at HP? So he gave two tables. One, or the second table is in which he gives HP would be so much based on the ground condition. So the first table is how to estimate the ground condition. I'll show you both the tables. And this work was based on two things. He did laboratory experiments, and he also carried out studies in a tunnel in Austrian Alps in 1920s. This was a 5.5 meter wide tunnel, steel arch supported. All tunnels were supported by steel arch there. So on the basis of this, he gave this. Okay, and the laboratory experiment was trapdoor experiments. I'm not going into details of this, which is mentioned here. But let's look at those tables. Table number one, in which he suggested how does one estimate the type, the ground condition. And the table number two would be for that ground condition, what would be the HP? And then you can design for that. I'll show you how to design. So he categorized the rock mass into 9 categories. Now, as I said, that this classification system has lost much of its relevance because of the technological advancements, which also I'll discuss with you pretty soon. But this table, you see, great people are known by their simplicity, as I said, but they have another hallmark. Whatever they touch, it turns gold, because they have an inherent class about themselves. It could be a God gift, or it could be sheer effort that they have put in honing their skills, whatever it could be. But these great people are great also because anything that they do, there's a class. They speak, there's a class. They do something, there's a class. You can see that. You can feel that class. So even after the relevance of their contribution has not applicable anymore, they do a few things which never fade away. This table is one of those things. You know how beautifully he has explained these 9 categories. Absolutely. It's a great learning curve, learning exercise. Anybody wants to understand rocks? Go through this table. Keep this table by your bedside. You know, now he explains 9 categories, starting from hard and intact. You know, hard, massive rock mass, hardly any joints, very wide space. And look at the description. The rock is unweathered. Obviously, if the rock has gone to weathering, it may not be intact or hard any longer. It contains neither joints nor hair cracks. If fractured, it breaks across intact rock. So intact rock, not along the joints. There are hardly any joints. After excavation, the rock may have some popping and spalling, rock burst kind of thing. Hard rock, if it's under stress, yes, popping and spalling, and might be rock bursting, which is what he mentions. At high stresses, spontaneous and violent spalling of rock slabs, which is rock burst. Hard, stratified or schistose. You have some layers, some joints coming in, and he explains. Massive, moderately jointed. Look at this. A jointed rock, the joints are widely spaced. It's not very close. Joints may or may not be cemented. It may contain hair cracks, but the huge blocks between joints are intimately interlocked, so that, you know, all this description. And the quality keeps falling down. Moderately blocky, very blocky, completely crushed, and all that stuff. And you come to squeezing down condition, poor rock. So from rock burst to squeezing. And swelling, which I did not discuss. Swelling is also a problem in tunneling. You see, Swelling is as bad as squeezing, enormous pressure, etc. In swelling, if the joints or the crock has clay minerals like montmorillonite, illite, kaolinite, given access to water, these minerals swell and they can put enormous pressure on the support system that you install. And that's why in typical tunneling investigation scheme, a test for presence of these clays is become a standard now. You basically carry out what is called an X-ray diffraction test, which is becoming in standard because this could be real. So he did this. Now all this is 1946, 74 years back. So that's the contribution. Now let's come to second table. So from this table, for example, you're going to put a tunnel as a designer and you see, okay, from the description, I am in category 5. As an example, category 5. What is the HP height for category 5? You go to second table, you will see these parameters. This is the tunnel with a width B and height HT, T for tunnel, and you have an overburden above the tunnel of height H. But this entire weight doesn't come on this. Remember, yesterday we looked at the arch effect. You see, whether it is Pietro Lunardi or Karl Terzaghi or Evert Hock or NATM or NMT or Ravi or Alpha or Shakir or anybody, doesn't matter. It is nature. Nature. You can look at the nature with your own glasses, but the nature behaves the way it wants to behave. So an arch effect is kind of discussed here. So which means the entire weight of the rock mass doesn't come. If the entire weight was to come, Gotthard Base Tunnel at its deepest 2.3 kilometer, 2.3 kilometers, 2,300 meters multiplied by 2.7 tons per meter cube. That is the pressure you're talking about. Rohtang Tunnel in India, inaugurated in October first week, 1.9 kilometer at its deepest, 1,900 multiplied by about 2.7 tons per meter cube. That is in tons per meter square is the pressure. Can you build a tunnel? Absolutely not. The moment you build the tunnel, it will get crushed. Obviously, the entire load is not coming. Okay, so this is the height, equivalent height for which the load is coming. That's what he said. So HP, how do you know HP? Suppose you are in category 5 from the previous table. You go to the next table, 9 categories. You are in category 5, very blocky and seamy. The HP value is given by this. Ranges from, range again, in geotechnical engineering, you got to get used to ranges. You don't get precise numbers. 0.35, which is one value, 0.35 to 1.1 multiplied by B plus HT. For example, if your tunnel width is 6 meters and tunnel height is 6 meters, as an example. Okay, let's put it this way, 5 meter, 5 meter to make it simple. If this factor is 10 and you are in category 5, so HP would range between 0.35 to multiplied by 10, 3.5 to 11 meters. 3.5 to 11. So what is the pressure? This value multiplied by the unit weight of the rock mass. Average unit weight is 2.7. It could be more, it could be less, but usually 2.7. 3.5 multiplied by 2.7 tons per meter cube gives you a pressure of whatever value, and that range you get. So you can design for that range. How do you design? I'll tell you later. So similarly for other categories, you can find out. So that's once you know the pressure, you can design a shortcrete lining, a rock board system, a steel arch, etc. So that was very handy, and people lapped it up. So for years and years and years and years and years, well into 1990s, lots of tunnels were designed using this. I was involved in design of many tunnels using simple approaches. Now what has happened? Since this approach was developed based on a tunnel which is 5.5 steel arches. So one of the limitations of Terzaghi's theory is that it may not be applicable for tunnels wider than 6 meters. It was so popular, it attracted attention of researchers, and many people did many things and came up with their own comments on Terzaghi's approach. It was so popular. Now, Deere, or Deere, I don't know how to pronounce it, Deere. In fact, we lost him just the last year. In last couple of years, as I mentioned, many stalwarts of rock mechanics have left this world, and Deere was one of them. He is known for introducing the concept of RQD. We'll discuss more about RQD later in this presentation. So what he did, he modified Terzaghi's classification system, the tables that you saw, and he introduced one column with RQD. And there's a table coming. Also, what Deere did, because see, everybody was trying to make life easier for the designers. Terzaghi made it very easy. And you see, it's so difficult to come up with your own original things. Great people do that. And then once you accept that, well, this is a great job that somebody has done it, then you kind of add to that. That's the most sensible thing to do. If you can improve that, and that's what many of these people were doing. So what Deere did, Deere included RQD. I'll show you the table. And he also differentiated in that table between, because TBMs had started to come. This 1946 note, I mean, tunnels were built using TBM in 1853. But the TBM started becoming popular in 1940s, 50s, 60s particularly. In late 60s, early 70s, soil TBMs started to come, but rock TBMs were there. So in 1970, Deere included RQD plus differentiated between TBM excavated tunnel and drill and blast excavated tunnel, which is also mentioned in the tables which are coming up. This is what he did. Included RQD in Terzaghi's table and modified these HP factor to some extent based on further experience. Okay? Don't worry, because you're not likely to use this system. You're most welcome to do that as an additional system and check. And this is what he contributed in terms of introducing these TBM drill and blast, TBM drill and blast. And he said, based on the RQD range and the construction method, you could choose these support systems. So he brought in Terzaghi's time, there were no rock bolts used in tunnels. Steel sets, rock bolts, shotcrete. So lots of things. So this made the life further easy for designers. But it's all based on experience. And why is this approach not that relevant now? For two reasons. At that time, the Terzaghi's approach was very successful. But two things changed in modern times. One is the blasting techniques, drill and blast method, which we discussed the other day, has improved a lot. Second thing is the support system concept has completely changed. I'll explain these things. Back in those days, blasting was not as sophisticated as it is now. So introducing weaknesses in the rock mass was common because of blasting. Blasting would further weaken the rock mass, introduce more cracks, etc. The controlled blasting techniques, the smooth blasting techniques were not there at that time. But now everybody wants to obtain a smooth periphery, wants to minimize the overbreaks, underbreaks. The drilling techniques have improved with jumbos and other computerized equipment. You can have better drill pattern and therefore better results in blasting, etc., etc. So the damage which was done by blasting is much less now, unless you have a completely careless contractor and a completely ignorant client. That practice of little primitive kind of blasting technique, as I said, lowered the strength of the rock mass and permitted more convergence. A weaker rock mass will converge more. We know that. And also the creation of loose zone because of blasting. But now that is much improved. But in projects where you have similar conditions, poor blasting, damage due to blasting, yes, Terzaghi is still applicable. Second is about the support system. The support system that time was steel arches. As I mentioned the other day, this is a passive support system. It doesn't reach out to the rock mass. See, blasting, overbreaks, underbreaks. Steel rib, smooth. It's not in touch with this. By the time the rock mass comes in contact with steel ridge, much movement has already taken place. So, a good support system is that the moment you excavate the rock mass, the support should prevent any further deterioration of the rock mass. Steel ribs don't do that. They wait, allowing further convergence, further deterioration. So both these practices of the blasting at that time and the concept of using steel arch rigid support systems weakened the rock mass further. Now that's not the case. In fact, people now say that the support pressure does not increase directly with the size of the tunnel. In the same ground condition, if you have a 6-meter tunnel or a 10-meter tunnel or a 15-meter tunnel, The support pressure will not change. The load will change, but pressure is load divided over area. That will not change with this opening. Okay, but during Terzaghi's days, it used to change, and that's why the table shows changes with the size. With the size, the HP is changing, which is not the case now. And in fact, Barton, I mentioned Nick Barton, and today we are going to discuss Nick Barton's Q system. So he said in 1974, 1973, sorry, yes, said that support pressure does not depend on the width of the opening. Opening means the tunnel, rock tunnels. Later in 1993, I found out that support pressure is really doesn't depend on the tunnel width, provided you do not change the support stiffness. If you plot the support stiffness, stress in relationship, if you don't change that, which means larger opening, you have to use more support, so the stiffness is not changed. If you maintain that, then support pressure doesn't change. Because I found out that if the size increases, but the support is the same, the support pressure increases. So later on, my colleagues, my dear friend, my batchmate, and my companion during our bachelor days before marriage, and we used to share the same room, used to cook our food together. We learned our tunneling together. R.K. Goel, Dr. R.K. Goel, who is very famous internationally. He's written, I think, 4 or 5 international books on tunneling. So in 1996, he also studied this aspect and found that what I'm saying is incorrect. That's how the research develops, no? And he said, there is a negligible effect of tunnel size on support pressure in non-squeezing ground condition, elastic ground conditions. But the tunnel size does impact the support pressure in plastic ground conditions. So he sort of improved, or sort of said that what I'm saying, what Verman is saying, is only correct for elastic tunnel. Once the plastic zone starts to happen, in this case, squeezing means, in this case, plastic zone is there. So all that happened, but as I said, if you read about these things, it'll give you more insight into the tunnel behavior. Later on, Singh and Goel, Bhavani Singh, one of my supervisors, PhD, and of course the same fellow, Dr. R.K. Goel, in 2006, they did further studies and found out that Terzaghi's method provides reasonable support pressure for small tunnels under 6 meters. But if the tunnel is more, because in 1990s onward, bigger tunnels started to be constructed. If the tunnel diameter is from 6 to 14 meters, then Terzaghi's approach gives over safe estimates. And I can see the reason behind that. You see, although they did not elaborate here, Singh and Goel in 2006, but I think the reason for that is that these large size tunnels were more common in the new millennium, because lots of transportation tunnels started to happen. That was a major change. And their work, Singh and Goel's work, was largely confined to the Himalayas and Indian subcontinent, which is where the transportation tunnels started to come at the turn of the millennium, and some other countries. So these tunnels were built with modern techniques, modern blasting techniques, modern concept support system. And therefore, as I said some time back, Terzaghi's approach in any case was to be conservative, because now with these modern techniques, the damage to the rock mass was less. So Terzaghi's approach will overestimate. So that is also a part behind this. Okay, but that is not that relevant unless you find, and they will find many projects, the rock mass is still being damaged by poor blasting techniques. You are delaying the support installation. Check with Terzaghi's approach. Perhaps that would be more applicable in those cases. Now, so with that background, we go to, it's like, some people who are religious or spiritual, before they start a good work, they go to a church, they go to a temple, they go to a mosque to pray that to their respective gods, that, okay, I'm going to start this work, please bless me. That's what we did. You can't start a discussion on rock mass classification before without paying your respect to Karl Terzaghi. So having done that, let's move on to the 2 most commonly used classification systems, RMR by Binyowski and Q by Barton.